Hello. I want to talk about how to find the matrix of a given linear transformation. So if you know you have a linear transformation, how do you actually write down its matrix? We've seen some examples. It's not too hard, but there's a nice general principle that is worth pointing out here. So I'm going to show you that. So first, let's revisit an example from an earlier video. So it was this transformation T from two-dimensional space to three-dimensional space given by the following. So T of X, well, it's from 2D space, so that's really T of X1, X2. And that was defined as X1 plus X2, 2X1 minus X2, and 3X2. And we could say that's, Y1, Y2, Y3, which is the vector Y, right? And I just want to remind ourselves that we can also rewrite this. I think I did this in the last video, but we could also write this in the form, this sort of form where we break up all the X1s and then all the X2s separately. So if we do that, we have X1 times the vector 1, 2, 0, plus X2 times the vector 1, negative 1, 3. Right? And even more so, this is actually one way we define matrix multiplication. So you can also rewrite this as 1, 2, 0, 1, negative 1, 3 times X1, X2. And if you like, this right here now is the matrix. This is the matrix of T, which we called C, I think, in the video that I did this example. And so really what we have is that T of X is C times X, right? Okay, so you might say, okay, well, that's how you find the matrix of linear transformation. You just sort of rewrite the transformation, right? But I want to show you another way to get at it, and it's going to actually be very useful. Sometimes we don't have explicit formulas. We might have transformations that we can define geometrically, and then the formula is not obvious, but it's still possible to find the matrix. So, but let me just point out the thing that we can notice here. So, well, I just want to notice what happens. We talked about the standard basis vectors, and we know that any X here in this example, X1, X2, we know we can rewrite that as X1 times 1, 0 plus X2 times 0, 1. So that is really X1, E1. We were calling them I hat and J hat, but I'm just going to use the more general terminology. X1, E1 plus X2, E2, where these are the standard basis vectors, right? E1 is the vector 1, 0, and E2 is the vector 0, 1. And so these are the standard basis vectors for R2. Okay, and so I asked that kind of, maybe this is not a great motivation, but it kind of makes me think, what happens when we apply T to E1 and to E2, right? So, if every X is built out of E1 and E2, then it might be interesting to think about what is T of E1, what is T of E2. So let me write that down. Every X is a linear combination of E1 and E2. So then, what are T of E1 and T of E2? Because that might help us think about what T of X is in general. And let's just try it in this example. So if we do here, if we do T of E1, well, that's just plugging in 1 for x1 and 0 for x2, right? So if we go all the way back up here, and we plug in 1 here and 0 here, 1 here and 0 here. So maybe I should really do it this way: 1, 0, 1, 0, and then, well, there's no 1, so 0. That's one way to think about it. Or you could think about plugging in here. You could think about plugging 1 here and 0 here, right? And either way, you can see that you just get this vector 1, 2, 0, right? Because if I make this 1 and I make this 0, this will go away, and I just get this vector. Okay, so this is 1, 2, 0. And similarly, you should stop and do it yourself. Pause the video and do it yourself, but what's T of E2? Okay, pause long enough. That's actually 1, negative 1, 3. And here's what's interesting about that. Almost off the screen of each other, but look at the matrix. Like, compare this to each of these. And it's like, oh my God, the first column is actually this guy, and the second column is this guy. So in fact, yeah, I could say these are the columns of C. And what we could say is, we could say, in other words, C is the matrix whose columns are T of E1 and T of E2, right? So that's the matrix made up. And this is the matrix for, and C is the matrix for T, right? C, oh, go back to the solid lines. So this is the matrix for T. And in fact, it's, so you somehow, just knowing what it does to the standard basis vectors, just knowing these lets us make the matrix. And my claim is that this is a more general statement. I mean, you could sort of imagine a more general formula. If I had something up here that was more, more dimensions, more general formula, but the same kind of idea, especially this part right here, would work, where you would just have, if I had a, a third, an x3 in here, and I had a plus x3 times stuff, here, having 1, 0, and 0 would just give you this vector again. So you can imagine this generalizes. So let me just write the general statement, and then we'll be done with this video, and I'll talk about applications. This works in general. Given a T, a map, linear transformation from Rn to Rm, we can find the matrix of T by applying T to the standard basis vectors E1, E2 through En. Since we start in, our domain is n-dimensional space, there's going to be n basis vectors, right? And so just to finish off, we can say that T of x is A times x, where A is the matrix whose columns are T of E1, T of E2 through T of En. Right. Just draw these vertical lines to make it clear that each of this represents a column of the matrix. I guess these are skipping columns, but yeah. Okay, and so, like I said, I mean, this is the statement, and this is a fairly general. One thing I would say is, first, check it against, check this against other examples that we've done, just to make sure it works. There was that video that had other examples, linear transformations, and you can check that this actually works in all those cases, or any examples you have in the book or anything. Okay, but then, and the application is we're going to actually, all the next few videos are going to be about geometrically defined. Let me just write that. So next, we're going to apply this idea over and over again. And I'll show you how, but let me just tease it to find, apply this to find the matrix for a geometrically defined transformation. And by that, I mean like something like a rotation or a reflection or a projection. Well, I'll talk about all these. So geometrically defined transformation. Okay, so go on to the next videos to see this in action.